Welcome. This is a two-part question. The first says, how much work is done by the gas in this expansion? So if we look at this diagram, we're taking a gas, an ideal gas, from being at a pressure of 10 Pascal and a volume of 1 cubic meter. First of all, down to being a pressure of 5 Pascal with the same volume of 1 cubic meter. And how do we do that? Probably by cooling. And then what we do is we expand the gas, and we go from 5 pascals at 1 cubic meter to 5 pascals at 4 cubic meters. And how do we do that? Well, the gas actually will want to cool as we expand its volume, so we must be heating it. So the first bit is constant volume, a cooling process, and then the second step is a expansion. And so we put heat in to maintain constant pressure. This is isobaric. The horizontal bit is isobaric. The vertical bit is isovolumetric. And conceptually, as I've shown in the question, actually, when I think about it, conceptually, the work done in this expansion, ignoring the heating and the cooling, the actual work done is the area under the graph. And we mean by that the area to the axis. And this is a 0, so there's my axis. Pressure vertically, volume horizontally. So we can say, well, in general terms, work done is equal to the integral of P dV, not VdP. It's got to be a change in volume. And in this case, we can see it's the area under the curve trace. So the work done in this case would be just this rectangular volume. But this would be 5 times 4 minus 1, which equals 5 times 3, which equals 15 joules. So the work done is 15 joules in this first case, which is this guy. In this second case, it's basically the same principle, all the same physics occurs, it's just that we don't have nice linear changes. What we have here is a change where somehow we get the pressure to follow the law, which says pressure equals 6 over the volume squared. So, okay. We can say, well, the work done is equal to the integral of P dV. And this is the integral, and this is going to be 6 over V squared dV. And this equals, well, it's going to be equal to, let's do one more step just to show it. So this is going to be the integral of 6V to the minus 2 dV. So the work done equals, this is going to be 6V to the minus 1 over minus 1. We increase the power and put it in the denominator. Which equals 6 over V minus 6 over V. And our limits are between 1 and 4, which equals minus 6 over 4 minus 6 over 1. And if I've got space, that's going to be minus 6 over 4 plus 24. So it's going to be, let's see if I can squeeze it in. This is going to be equal to minus 6 over 4 plus, because it's a minus and a minus, 24 over 4, which equals 18 over 4, sorry about this, which equals 4.5 joules. Which is that guy. So just, integrate the area under the trace, and sometimes you will get nice shapes like rectangles and triangles, and sometimes you'll get a function, and either way, you just work out what it is. It's a good idea when you get traces like this to ask yourself, how is it done? Rather than just treating it as like a magic graph. Just it'd be nice if you can look at it and say, oh, to go from this pressure with this volume to this pressure and this volume, I didn't expand or compress because there's no change in volume, so I'm going to simply cool the system. And then to go from this point to this point, well, if I just expanded the gas, it would cool, so I'd have too low a pressure. So that means that I must have heated. What I find a big thing is that superimposed on all these diagrams, and it's never mentioned, is there's a whole set of isotherms. They never get mentioned. And yet, if you can visualize them, it just makes so much more sense because this is temperature increasing as you go up. So there's a thought for you. Okay. So there we have it.